Okay. In continuation of previous lecture, we will solve some problems related to the Euler's theorem. So we start the first problem. So we have the statement verify Euler's theorem for the function f of xy is equal to ax square plus 2hxy plus by square. Okay, so here we verify the Euler's theorem. So we know that the Euler's theorem x del f upon del x plus y del f upon del y is equal to nf. Okay, so this is the LHS part of Euler's theorem, and this is the RHS part of Euler's theorem. So now first we write the RHS part. So first we write the RHS part. So for RHS part, we do just one thing, that means we have to calculate the degree n. So we calculate n. So we calculate n. So from this given function, so what is the value of n? That means we see that directly. Okay, this is the homogeneous function. Every term of the homogeneous function have same degree. So this is the degree 2. Second term also having degree 2, 1 plus 1, and third term have also degree 2. So this is the homogeneous function of degree 2. So here we can write down directly the degree of this homogeneous function is 2. So we write the value of n here, n equal to 2. So the RHS part will be 2 into f. F means given function. Okay. So now we need to prove the LHS part. So which will equal to the 2f. So now we take the LHS part. So LHS part, that means this x del f upon del x plus y del f upon del y. So now we give this as equation number 1. So first we do that means derivative with respect to x partially, and the second we differentiate 1 partially with respect to y. So differentiate 1 partially with respect to x. So when we differentiate equation 1 partially with respect to x, so we see that del f upon del f upon del x is equal to 2ax, differentiation of x square is 2x, plus 2hy, 2hy and plus by square. So y square we treat as a constant, so by square is purely constant term, so the derivative will be 0. So this gives us 2ax plus 2hy. So this is the del f upon del x. Okay, now differentiate 1 partially with respect to y. So when we differentiate equation 1 partially with respect to y, so this can be written as del f upon del y is equal to ax square. So a first term doesn't have any term of y, so derivative will be 0, purely treated as a constant, plus so the second term 2hx, the derivative of y is 1, plus by square. So by square means plus 2by. Okay, so these value we substitute in the above equation. So this you can say that we can consider as equation number 2. So putting these value in 2, in equation 2. So this x into del f upon del x equal to 2ax plus 2hy plus y del f upon del y 2hx plus 2by. So now we simplify this. So this 2ax square plus 2hxy plus 2hxy plus 2by square. Okay, so this gives us 2ax square plus 4hxy plus 2by square. So here we can take a common 2. So this gives us ax square plus 2hxy plus by square. So now we are solving LHS part. So directly we can use equation 1 here. So here we write down as using equation 1. So this gives us 2 into f. So this equal to 2 into f. So now this is our RHS part. So we have already solved the RHS part. So we can say that the LHS is equal to RHS. So that means our theorem is verified. Our theorem is verified. So this is our LHS, and this LHS is equal to RHS part. So, okay. So now this is our RHS part. So that means when we solve the LHS, so LHS is equal to RHS. You can say that. So this type of problem we will solve. That means when a question asked in the examination related to the verify. Okay, so we verify LHS is equal to RHS. We take one more problem related to that. Verify the Euler's theorem for the function u is equal to x raised to the power 1 by 4 plus y raised to the power 1 by 4 upon x raised to the power 1 by 5 plus y raised to the power 1 by 5. Okay, so this is our function u. Now we need to verify this as per previous question. So we write down as we know that the Euler's theorem in terms of u we can take as a dependent variable. So x del u upon del x plus y del u upon del y is equal to nu. So here we can calculate the degree because each term of the homogeneous function have same degree. So that means we calculate the degree of this particular function because this function given into the form of numerator upon denominator. So while calculating the degree of this uh, fractional term, so we write down as n is equal to the power of numerator minus power of denominator. Okay, so here we can take 20 as LCM. So 4 5s are 20 minus 5 4s are 20. So this equal to 1 by 20. So the degree of this particular function is 1 by 20. So now we put into this RHS side. So this can be written as x del u upon del x plus y del u upon del y is equal to 1 by 20 into u. Okay, so now we shall prove. So this is our RHS part we have proved. So now we take the LHS side. So then we prove this is equal to 1 by 20 into u. So now we take the LHS. So this is our RHS side. So now LHS is x del u upon del x plus y del u upon del y. Okay, so now we give as equation number 1 to this given equation. Now, so differentiate 1 partially with respect to x. So first we solve del u upon del x. So differentiate 1 partially with respect to x. So when we differentiate 1 partially with respect to x, so this gives us del u upon del x is equal to. So here we use the formula of u upon v. U upon v, that means numerator upon denominator. So we have the formula. So first we write down the denominator. So for doing differentiation, so denominator means x raised to the power 1 by 5 plus y raised to the power 1 by 5 into differentiation of numerator. So what is the differentiation of numerator? So with respect to x, so this gives us x 1 by 4 x raised to the power minus 3 by 4. Okay, and the second term is purely for y, so derivative will be 0 minus numerator. Numerator is x raised to the power 1 by 4 plus y raised to the power 1 by 4 into differentiation of denominator. So we differentiate denominator. So we have 1 by 5 x raised to the power minus 4 by 5. And the derivative of y term will be 0 because we treat y as a constant upon denominator to the whole square. So 1 by 5 plus y raised to the power 1 by 5 to the whole square. Okay. So this is del u upon del x. Now we write this complete term. So we write this complete term. So we multiply both side by x. So we write down as x del u upon del x is equal to. So when we multiply both side by x, so this 1 by 4 constant we take as firstly, so that we can write x raised to the power 1 by 5 plus y raised to the power 1 by 5. So here is the power x raised to the power minus 3 by 4. So we multiply by x, so power will be plus 1. So this gives us x raised to the power 1 by 4 minus 1 by 5. So x raised to the power 1 by 4 plus y raised to the power 1 by 4 into x raised to the power 1 by 5 when we multiply by x. So denominator will be x raised to the power 1 by 5 plus y raised to the power 1 by 5 to the whole square. So this is our x del u upon del x. So we have completed the first term. Now differentiate one partially with respect to y. So similarly, because we have the symmetry, so we can write down directly. Okay, we can write down directly, but you want to calculate, so you can calculate also. So we differentiate del u upon del y is equal to denominator x raised to the power 1 by 5 plus y raised to the power 1 by 5 into differentiation of numerator. The first term is x, so differentiation of x is 0 plus y. Y means 1 by 4 y raised to the power minus 3 by 4 minus numerator x raised to the power 1 by 4 plus y raised to the power 1 by 4 into differentiation of denominator. So 1 by 5 y raised to the power minus 4 by 5 upon denominator to the whole square. So 1 by 5 plus y raised to the power 1 by 5 to the whole square. So again we do the same thing. So multiply both side by y. Multiply both side by y. So we get y del u upon del y is equal to 1 by 4 x raised to the power 1 by 5 plus y raised to the power 1 by 5 into y raised to the power 1 by 4 minus 1 by 5 x raised to the power 1 by 4 plus y raised to the power 1 by 4 into y raised to the power 1 by 5 upon x raised to the power 1 by 5 plus y raised to the power 1 by 5 to the whole square. Now, when we calculated x del u upon del x and y del u upon del y, so now we write this as x del u upon del x plus y del u upon del y. So we calculate this value. So we see that the denominator of both the functions are same. So we can take a denominator as LCM. So we can take denominator as LCM. So x raised to the power 1 by 5 plus y raised to the power 1 by 5 to the whole square. Okay, so now first we write down the numerator of x del u upon del x. So this will be 1 by 4 x raised to the power 1 by 5 plus y raised to the power 1 by 5 into x raised to the power 1 by 4 minus 1 by 5 x raised to the power 1 by 4 plus y raised to the power 1 by 4 into x raised to the power 1 by 5. Okay, so we are adding this. So second term will be plus 1 by 4 x raised to the power 1 by 5 plus y raised to the power 1 by 5 into y raised to the power 1 by 4 minus second term minus 1 by 5 x raised to the power 1 by 4 plus y raised to the power 1 by 4 into y raised to the power 1 by 5. Okay, so first we take these two terms. So that means the coefficients. That means the coefficient of this term and coefficient of this term. So we take common. So we see that. So here we take a 1 by 4 into x raised to the power 1 by 5 plus y raised to the power 1 by 5 as common. So the coefficient of this complete term here is x raised to the power 1 by 4, or from this term the coefficient will be y raised to the power 1 by 5. Okay. So similarly, we do the same thing for these two terms, second term and fourth term. So we take minus 1 by 5 into x raised to the power 1 by 4 plus y raised to the power 1 by 4 as common. So we see that the first term is x raised to the power 1 by 5, or second term is y raised to the power 1 by 5 upon x raised to the power 1 by 5 plus y raised to the power 1 by 5 to the whole square. Okay, so we can take common from numerator. So this term and this terms. So we see that are common in both the terms. So we can take common x raised to the power 1 by 5 plus y raised to the power 1 by 5, and x raised to the power 1 by 4 plus y raised to the power 1 by 4. We can take common, and the coefficient of first term is 1 by 4 and the coefficient of second term is 1 by 5 upon x raised to the power 1 by 5 plus y raised to the power 1 by 5 to the whole square. So this term will cancel the power. Okay. So now we have 1 by 4 minus 1 by 5. We write down that this is 1 by 20 into x raised to the power 1 by 4 plus y raised to the power 1 by 4 upon x raised to the power 1 by 5 plus y raised to the power 1 by 5. So this is our u means equation using equation 1. So this gives us 1 by 20 into u. So this is equal to the RHS part. So we have a verified. That means we proved, or we can say that the verified. So we write down as verified. Okay. So now last question we take as, if u is equal to log x raised to the power 4 plus y raised to the power 4 upon x plus y. So then prove that x del u upon del x plus y del u upon del y is equal to 3. Okay. So we write down a solution. So that means u given, u is equal to log x raised to the power 4 plus y raised to the power 4 upon x plus y. Okay, so we cannot calculate the degree of this function directly. So we take a logarithmic into the LHS side. So we take the anti-log. When we take the anti-log, so this gives us e raised to the power u is equal to x raised to the power 4 plus y raised to the power 4 upon x plus y. So here the u will change into the fu. So this u change into the form of fu. Okay. So now when we calculate the degree from this function, so the degree n is equal to degree of numerator minus degree of denominator equal to 3. So by Euler's theorem, so we have a x del u upon del x plus y del u upon del y is equal to nu. So here u replaced by fu. Fu means e raised to the power u. So we write down as x del upon del x into e raised to the power u plus y del upon del y into e raised to the power u is equal to degree is 3 into u, e raised to the power u. So when we differentiate e raised to the power u with respect to x, so this gives us x into e raised to the power u del u upon del x plus y e raised to the power u del u upon del y is equal to 3 into e raised to the power u. So here we take e raised to the power u as common. So we see that x del u upon del x plus y del u upon del y is equal to 3 into e raised to the power u. So we can write down this as x del u upon del x plus y del u upon del y is equal to 3. Okay, so that means 3 e raised to the power upon e raised to the power u. So 3. So okay, so thank you.